goes by the name of parallel water photo-oxidation reaction pathways in hematite photoanodes, implications for solar and fuel production. So,
yes, thank you, Paulo. I really thank you and appreciate a lot, Thomas. I'm really glad to be here in your seminar, and for me it's really very exciting to stay here in CUSEI, because I made the bachelor in physics. Here started all the adventure. I remember the first time that I arrived here, and for me it was like a very big place. Each course, math course, it was a challenge, and now it's for me it's very impressive to be now in the seminar and in the in a talk here in the auditorium of this place. Okay.
just to share your screen.
Okay.
Oh, the other one.
¿Esta?
Yeah.
Okay. Okay, so thanks for the invitation. I also enjoy a lot to see the faces of my friends. It's awesome. Okay, I want to talk about a topic. It was my research project when I was living in Israel. I was living in the city of Beersheba. Probably there is a very large name. I hope that during this talk you can understand more or less what is about this name. But in the first part, in the first part of the talk, please only take this implication for solar fuel production. In the second part, we will see the other thing that it seems more cumbersome. Well, I was. There is a mouse which I can. Should I put another way to see the complete? It's okay. This is Israel. This is the Mediterranean Sea. In the central part of Israel is where Tel Aviv is located. I didn't want to use the cursor, but Tel Aviv is located in this area, like the central part of Israel. Jerusalem is at the west. Is near to the. This is nearer to the border with Jordan. Here in the border is exactly in the middle of the Dead Sea. And I was living in a city that is called Beersheba. It's exactly in this part, Beersheba. But our institute was not in Beersheba exactly, but our institute was like 40 kilometers at the south. That is called Zeboker, and it was a very strange place, but beautiful also. Here is the institute, and here was the solar energy building where my office was located. The project, I was invited to participate in a project more something like applied science, to work with another group that do experimental research on materials that is related to renewable energy, and in this case with solar energy. But at the end, we could we were it was a process of 2 years and a half almost, and at the end it came out this paper that was published in Energy and Environmental Science. This is one of the most important journals of energy. Maybe if not the first, the second most important. Maybe this has an impact factor like 38 or something like that. It's like it was for us. It was like a great achievement to accomplish it. And the research group was was formed by two groups, the experimental groups that work in the Technion. Technion is one of the most important universities in Israel that is in the north, in Haifa. Abner Rothschild was the boss of the chief of the group. He's one of the an important person in topics related to this type of technologies. I will explain it further. And Anton, he was a PhD student, and he was the one who performed experiments directly, and then he was a key part on this project. Actually, we all the topic we built it first with Anton and I, and then we showed it to the other parts of the group to to encourage to go in this direction. So it was key of this. And Ifat Pipner, I didn't know this guy because he worked after he got in the project after I left, but he is also part of the experimental group. And I was working with Arik Yohelis. He's a theoretical physicist. I was working with him before about pattern formation and another systems with diffusion, and now we participated in this project. And he was the one who invited me to work with, so I went to Israel. Okay. Well, now it seems that it's a completely different topic, but the point is that all the efforts, the scientific efforts to go in this in the research of energy and different sources of energy and renewable energy usually are linked to social problems and to social problems that we're facing different times. The technologies that I'm going to talk about that has to do in how to get hydrogen from solar energy is a technology that was invented first, or like in the 70s, because in the 70s, in 73, there was a crisis of oil because there was an embargo of the Arab countries. They made an embargo to other countries about the conflict in Israel. Actually, it was a and this embargo got red flags in different countries, and they tried to explore and put a lot of money to explore different technologies. Then in the 70s there was a boom of researching in different type of technologies of energy, like renewable energy. Another boom was made in the 90s due to the war of Iraq, the Iraq war and everything. And now in the last 10, 15 years has been another important boom due to the global warming. So here I put the time series of the level of carbon dioxide in the last thousand of years. It's almost a million of years. Global warming is okay. Well, we know this type of things. The point is that up to now, it seems that all the evidence points that the emissions of carbon dioxide and due to the human behavior is the thing that can have been able to explain the global warming, not by models with other things without the human behavior haven't been able to explain it. And there are projections about what can the next scenarios. So this type of projections now had put a lot of interest to see ways to how to change it, and there is a lot of budget to for technology, for the research and development of technology. Okay. Just to have a.
Sorry, Paulino, can you go back to the slide of the time series of this carbon dioxide emissions from the last one? Previous one. So it seems to me that like if there is something periodic going on there, right? Because you see these ups and then downs and more or less with the same. So this could be related to I don't know, something in the earth, natural stuff.
Could be. I mean, actually, I'm not expert on this, so I cannot give an answer, a real answer on this. But the people had investigated about different periodicity, stellar periodicity, for example. I don't remember all the different movements, but there are periodicities of long term, of very long term. I don't remember what are these type of movements, astronomical movements. Could be that, or could be different things. I don't know.
I cannot see that what is between the x-axis.
Years before today.
So, what is the x-axis? How many years it is?
This is 800,000 before today years.
Okay. Then the next one is 700,000. Right?
Each
100,000 period.
800,000 before today, and here's 0 years before today.
And do you know how it is estimated that levels of concentration?
Yes, that's
No, I took this from the
This time
NASA.
we have direct measurements.
Yes.
I think that that's what they do with, these paleontologists and all. They can measure in stones and something like that.
Yeah, but
Some of them are in ice also.
Carbon dioxide level we have.
Maybe it's related with the ground, within the ground. Something more. Because, people used to know about all the things that happens when this, for example, this meteorite and the dinosaurs, and they can know what kind of environment was there in that time just by looking at these layers in the
They
ground.
can estimate what kind of.
Yeah, maybe the carbon storage.
Yes.
Maybe the carbon storage as well.
Yes, for example, I remember that in the North Pole or in the ice, in glaciers, or they get. But I don't remember if this type of studies in the ice they go as long as this. I'm not sure. I don't remember. Sorry. Okay, so this is like the different like CO2 emissions by type of fuel. Most of them are because of the carbon, and this is coal, no carbon in Spanish. It's carbon, but this is coal, oil and gas. This is like the global consumption by source, and also we have coal, oil, and gas, and the other resources are a very small proportion. And of course, we can see also here how increased the consumption of energy in the last 50 years. I mean, it has increased. Okay, it's a lot, but then this is only the production of electricity. And in electricity, we have also coal, that is one of the most important sources to produce electricity, and gas. In Mexico, also, we use coal and gasoline, but we made oil and gasoline. Oil as gasoline and coal, but in times of the President Fox, there was a important transformation of the factories to change all these power plants to change it into gas. When Texas made this, how they call this way of production, well, Texas started to produce very cheap, so that was the strategy. Okay. Here I show two different ways that now we can see of how to take advantage of solar energy. one is natural and one is not. The other one is not natural, right? Here I put the photo of a power station, a solar power station that is in Israel. Actually, it was in the way to my institute. So I twice or three times at the week I saw it. It was impressive. Actually, there they call it like the Eye of Sauron, like because it's like it's a lot of the rings. Because this now it's not in the photo. This light you see at the top. So you see the tower and the top of light that is you cannot see it directly. It's this little bit at the beginning. It really scares. This is something impressive. And here is a photo of the same power station. You can see the different mirrors. There is a lot of mirrors that all of them are around it, and everyone points to this storage of water or something. I'm not sure what is the liquid that they take, but not all the mirrors, but a lot of mirrors points there. They are controlled by some computer. They cannot point out all the mirrors because they can burn the stuff. So sometimes that's why we sometimes see this, that they pointed to another part, but this is not a good thing for the birds because there are a lot of birds that die there, really. And this is amazing. In the time, this was the tallest solar power plant in the world. Now there is another one. But there is a problem. Still, this form of taking solar energy there is intermittency in the uses of this because you can use it during the day. They also have another system there, like there is solar energy, and also they use like heat energy when the sun goes down and everything. But anyway, they cannot use it in a continuous way. And the big trouble or the big problem to solve is how to get solar energy and use it to produce electricity, particularly to produce electricity in a continuous way. And the point is how to store this solar energy in order that we can use the solar energy also in the night, because the night is the time when we use more energy. So and here in the other side we have a natural process, and this natural process do exactly what we want. The trees storage the solar energy, and that's like an important part that we want to learn. I mean, we have the notion that it is possible to storage the solar energy. There is a process. Well, of course, it's the photosynthesis. So there is a process in which, due to the photosynthesis, they split the water into oxygen and hydrogen, and then there are more processes. But okay, but this splitting of water is something important. Now, there is for all that have studied science of chemistry, probably you know what is electrolysis of water. And this is an important part of the next or the technology that I want to talk about. Electrolysis of water is a technique that was developed like 200 years ago. I'm not sure that what they do is to separate the water. It's a way to make the water that you can separate it in hydrogen and oxygen. And that's the idea. How you can do it? You only have to put two metals in the water. These two metals, you have to connect it with a voltage. How do you call a voltage source? A power source. And this is like you know this guy here in Mexico in the bars that they say, "Hey, toques." These guys have a little machine. There's a power source that you can regulate. So you regulate it. If the voltage is not enough, there is no reaction and nothing happens. but there is a limit when the voltage is enough, is big enough, so the reaction starts to appear, and you see things here. When reaction appears, then you are separating the water. And so I will show the music for the no. Okay, here they have two wires, and here these are the metals. They connected to a power source. These these metals, we call it, one is the anode and the other. These metals are the electrodes. One is the anode and the other is the cathode. The anode is the one that has in positive charge, and the cathode the negative charge. And sorry. And these bubbles that you see is because the reaction is actually happening, and the reaction is happening actually, and the bubbles is because you have the gas. In one side the reaction is producing oxygen, and in the other side the reaction is producing hydrogen. So to gather energy, the oxygen, you don't care about the oxygen, so you leave the oxygen goes away, will go away, and the hydrogen you keep it, and you can save the hydrogen, and it's very cheap to storage the hydrogen, because you just do it in how do you call a tanque? Oh, there is another word. Chamber. How do you call something? Chamber. Chamber.
Like the cylinder stuff.
Container, yes. Chamber. Chamber. This for the gas. This cylinder.
Gas chamber.
Gas chamber. Okay, thank you, sir. Yeah, you said it in a gas chamber, so you can, or in the big containers for gas. I mean, this is cheap to storage, so you can keep the hydrogen. Now, what is the advantage about global warming? Okay, the point is that usually, if you get, for example, natural gas, there is much better about the CO2 emissions than gasolines. But if you want to, for energy, explode natural gas, it's a reaction of methane with oxygen. So you have the explosion. So and you get CO2, is what we don't want, and you get water. But if we have hydrogen and we want to explode the hydrogen with oxygen, we get explosion, but we get only water. Now, water is also a gas. How do you say it? Invernadero?
Greenhouse.
Greenhouse gas. Thank you. It is also a greenhouse gas, but it's more easy that goes down to the earth. I mean, with water, we have a cycle of water that is not so harmful like CO2. And okay, and now what is the proposal? This is the technology that we started to explore in the 70s. The proposal is that we make this type of electrolysis, but assisted with the sunlight. And the idea is that instead of having a metal in the anode, we put a semiconductor, with which a semiconductor is a material that can have properties, the different properties, and can have properties of also like metals for the conduction of electricity, for example. So we have a semiconductor that can absorb the energy of the sun, and this aids a little bit or push forward the reaction, so we can have the reaction at lower potential than the potential that is required to do electrolysis. As I told you before, the electrolysis happens if the potential is big enough. But the point is this: we can gather hydrogen, but we need money to have the energy to separate with electrolysis. So we we do not gain there. So the point is that with the aid of the sun, you can use less, you can use lesser potential in your machine. So it could be, so you can earn energy. I mean, and it can be convenient for the industry, etc. So the big aim of the research one of the big aims of the research in the world about this topic is how to do this technology that you can see in this diagram, is how to make the things so you get the reaction of water splitting, you get it with very low potential. And nowadays, no one has achieved that. For having a reference, I will put here in the board. Usually, you need, for example, this here is a potential, a reference. Let's say 0 potential. There is only a reference. There is not a real 0. Usually, you need to get to this potential to get electrolysis. And with the current technologies to use the sun with semiconductors, now the people are getting the reaction like in the half of the potential. You can get the reaction like here. But to be viable for the industry, you need even less potential. You need to be like at the half of that, more or less, to have a reference. So all the technological grades and the different laboratories try to know how to achieve this, to get the reaction with this low level of potential with the aid of the solar energy. That's the big objective, and eventually they will achieve it. I mean, eventually I think that this will happen. But nobody knows if they will achieve it in 10 years, 40 years, 80 years. Is something that is difficult to know out. And now, why they think it is possible? There are technical reasons that they know that is what I will tell after. But it seems that we are kind of close. We see some properties of the materials that it seems that it is possible really to have this, but there are obstacles, and the people are trying to get rid of the obstacles. And what else should I do? And one part of the difficult thing, the main part of this, it has to do with the oxygen evolution reaction. I mean, with this part, because it's the part when we have the interaction of the sun, and this is the part where the things. I mean, this reaction is a reaction much slower than the hydrogen evolution reaction. So this is the bottleneck. If we can make a quicker oxygen evolution reaction, we can do the thing. But the point is that this reaction, no one knows exactly what it is. The reactions to do this technology, this is the same in electrolysis. You see the video of the electrolysis that you can produce oxygen and hydrogen, and this can happen because you have cyclic reactions in the anode and in the cathode. And you could ask why, how we know that there are cyclic reactions? Because if they weren't, you would have degradation of the material. If you have a reaction that is not cyclic, now instead of having this copper wire or something like that, you will have this will have a rapid degradation. So what happened in this type of reaction is that happen different reactions that at the end it comes back to the first material. And this cyclic reaction happens so quickly that it's very difficult to measure where the species that comes in these cycles. So it's difficult to know what are the reactions involved. And if we do not know what are the reactions involved, then it's difficult to hack them to get with what we want to do. So part of the science and the things that we were trying to do is try to understand better the process. And it's like the main part of the main idea of the project. I hope that from now everything goes well. Okay, okay. Now,
Just one thing.
uh-huh.
So you think that we haven't gone through this transition to using hydrogen as a fuel for doing stuff just because of the physical difficulties, or because I would think that there are also economic and all stuff related to that. I mean,
Okay.
going out from oil and
Yes.
stuff like that is not.
But the point is that now it's not cheap to produce hydrogen. That's the point. But if this technology advances and we can use the sun to get hydrogen, the
So
things
if we
will
have
change.
that running, then the other stuff could eventually happen.
Yes. Yes. Yeah, because now we can get the sun to have not intermittent
Mhm.
energy. Now here I show the specific arrangement in the laboratory. I'm not an expert on this because I was in the laboratory only a few days to visit and to see and but I'm not an expert. This arrangement of this type of things are here. They put this in this type of thing that we call a cappuccino cell, where the light comes in this type of lens, and you put the electrodes. The cathode is fixed, but you put the anode, and you can put it in like it's a little it's a little how do you say placa? Plate. Yes, like a little plate, a very small plate, but at that plate you put a small layer of the material that you want to test as anode. So this small layer you have to do it with another machine to do the position, and it's very interesting. With the material that we use here, and then that this was the main part of the research, it calls hematite. That is a type of iron oxide. So you make the deposition and then you put it in there, and then here is a machine that is used to mimic the solar light. So and then then the solar is connected, and also the power plant that is controlled here. So you have potential that you can move at will, and well, it's with a computer. And here, what you see is not the emission of gas. Here, you do not control the gas, or you not set the gas emitted, but what you measure is the current. When you have a current, it means that the reaction is happening. If you don't have current in the circuit, then you don't have the current is in this circuit, then you are not having reaction. So and it's a very precise measurement in the sense that you can measure, you control the potential, and you can measure what is the current that is in that potential. So you start with zero potential and you start to increase the potential, and if there is no current, there is no reaction. There is a point where the current starts to rise. So you say, okay, here's the potential, and seeing the current, you can see properties of your reaction. So this is one of the things that in these experiments can be done. Here is the type of voltammogram that you can get. Here we have three. The colors are with different type of material. It's not important, but in these curves is then the normal electrolysis. The standard electrolysis without light, without semiconductor. No, it's with the semiconductor, but it's without light. So you have the reaction at this potential. But if you introduce the light, then you can get the reaction with lower potential, and that's the thing that it can be measured in this type of experimental arrangement. Okay.
Sorry, maybe I missed.
Yes.
So what kind of light is it? Visible light or some?
In this article, I don't remember, but it can be used. Usually are visible lights. Usually it's lights that they try to mimic the sunlight. Usually they control particular frequencies or particularly. It depends on the experiment.
So experimental arrange is semiconductor in the anode, metal in the cathode, or what is in the cathode?
Yes, I don't remember what they use, but there is something standard. I mean, the cathode is not a variable that they move. Why? Because the slow reaction is the reaction that happened in the anode. It's much slower than the reaction in the cathode. So it's like the bottleneck, we have it in the anode with the oxygen evolution reaction. So that's what they move.
Do you remember what semiconductor is?
We use hematite.
Hematite?
Hematite that is a kind of iron oxide. I will show it the hematite particularly in next slides. But this is a very promising material that at least in this group of technical they think that this could be like the one maybe. Who knows? The first semiconductor that they used at the beginning in the 70s was oxide of titanium oxide. This is what are most popular, and there are more, right? Okay. Now we start another part. Is like what are the solids? I will talk a little bit about the solids to talk about the semiconductors and try to describe the specific problem, but it sometimes takes time. As some of you know, maybe most of you know, but the solids are here is in Spanish, but it's like a crystalline structure that we have molecules that are tight, and they cannot move freely. But you have the nuclei of the molecules are the ones that are vibrating in some positions, and you have a lot of electrons. Sometimes the electrons are bounded to its own nucleus, but some other electrons are not bounded. Some other electrons are just wandering around this structure. So with the electrons, you could make like statistical properties of the electron. For example, measure the energy. Imagine the energy is similar as we measure like the velocity of the distance about the nucleus or something like that. But you can measure the energy of each electron, and in a line, you could say, okay, this electron has this energy, this one, this energy. So here you can have, you gather electrons and put it just to measure what energy, and usually are not distributing uniformly, but they can have a kind of bands of energy. And there is another band that is up every one. And so the energy of the electrons is seen like these bands. Some of the bands we call valence bands, that are electrons that are still around its own nucleus, and other is conduction band that are not tied to some nucleus. And usually there is a band gap between the last of the valence band and the first of the conduction bands. And this is what for. The point is how the solar energy and the semiconductors works to do this type of things. What happens is that there is from the sun, it comes a photon, that is a particle of light that comes to the material, and the photon hits an electron that is in the valence band, and so as it hits, gets higher energy, jumps to a band of conduction. So this electron now is wandering in the material. So the material has now properties of conductor because of the action of the sun. We call this a electron hole pair, because we have an electron now in the conduction band, But we have something strange here, like it's a hole, and this hole acts like a bubble in the sense that you have an effective positive charge here, and these are going to things that are key for how they work, these type of things. If a hole is created, and if we have a potential, this potential make as is an effective positive charge, then this charge also moves and can move and can have a drift this hole, and that's and now what this for? Because what happened, this is the material, in this case the hematite that I will talk. The sun hits the material, the semiconductor. Usually when the sun hits the material, do not hit just in the surface, but the sun goes through the material and hits inside the material. So inside the material are creation of electron hole pairs that are created here, the electron hole pairs. And as you have potential connected, the potential will make a drift. The electrons in the conduction band goes in one direction and the holes to the other direction. In the anode, the holes go to the surface where you have the electrolyte, that is the water, and is what you want. You want that the holes go to the surface, because if the holes go to the surface, then a water molecule can get absorbed to the surface. And when the absorption occurs, a reaction occurs. And that's the process that we are interested in. Now, this process has different steps that is difficult to have a efficiency in this process. So first, we have an absorption efficiency. What does mean? This means that from all the photons that hits in the material, what proportion of those photons make an electron hole pair? So we have a proportion, and this is the first efficiency, and we lose something there. The next is the charge separation efficiency. That is, okay, now when there was a electron hole creation, you need that the holes goes to the surface of the electrolyte. So, but sometimes the drift is very slow, and they go back again. The hole is filled with the electrons in the. I mean, they fill a hole before the hole arrives. So this is we lose a lot there, and this is the charge separation efficiency. So if they when this happens, we call recombination. They recombine again. So what we have gained separating the holes, then is lost again. So you need that the charges can be separated. Now, when you after pass this step, after this step is, I mean, the holes that arrive to the surface, here are a lot of holes. There is a proportion of holes that indeed have a reaction with the water. I mean, that they have this absorption with water, so the reaction happens. So this is the next efficiency that we want, and as is actually the efficiency that in this work, and we want to understand, or is that important, this step, and also in many of the labs. I mean, this is the step that many people try to improve. From the hole that arrive to the surface, how many of them get the reaction? Because if the reaction is done, you are making the transformation that you want. The transformation of, well, I mean, this is the next step, but first is how many holes get the reaction with electrolyte. And the next efficiency, the Faraday efficiency, it means how many of these reactions gets transformed water into oxygen. So this is the whole process. So it is kind of difficult. Okay, now this.
And I see.
Yes, of course.
So I try to understand the several steps in this sequence.
Mm-hmm.
So in the third one, you have these hole tubes to the surface. But what about the electron flux to the surface? So which is bigger, which is slower, and how do you know that? Because you don't mention it here.
No.
How do you know that is more relevant, this whole flux than the electron?
Yes, it can be measured. The electrons goes to the cathode, and in the cathode we have the electron go to the other side. Also, you have the
I think you sorry, you put a static potential or something, and you would get positive, you will get negative charge when pulling out.
So they are taking
Positive
out of the
charge.
semiconductor and flux to the other end nodes.
and in the ends, in the extremes, it's in the cathode. You have a negative part, and in the anode the positive. In the negative part, the reaction of hydrogen is much quicker. But the step that makes that the process cannot go around is this one. This is the bottleneck. So
So this is the current that you measure.
yes, the global current. But this is stocked, then you don't have current. You need both. So now his hematite. This is a kind of oxide. There is abundance of hematite in the earth. It's cheap. You don't have degradation in the if they are in water. Like it absorbs a lot of solar energy. The absorption is good. So there is a lot of reasons why hematite is something promising to do this thing. Here are the properties. Is hematite's abundance on Earth, non-toxicity, high photochemical stability. It means that it do not get degradation when the reaction is happening, and narrow band gap. The narrow band gap it has to do with how many energy you need to get the reactions. I will show. Okay. Here, the poor oxygen evolution reaction kinetics of the hematite is exactly the here they say there are the major challenge limiting solar conversion efficiency. I mean, it's like the thing that they try to I mean, the point to achieve is to have a faster oxygen evolution reaction, because it's the thing that is limiting getting the conversion. Because nowadays they need a large applied potential, and this is what we want to reduce. And a nano and photoanode based on hematite that accomplish the things that we want, and hasn't been founded. I mean, hasn't been reported this achievement, and also with other materials. But it's something that although hematite has very nice properties, it still needs this last part of the charge for the reactions. The holes in hematite, they do arrive to the surface a lot, but at the end there is a last step that cannot make the reaction as quick as we want. Here are the band gaps of different semiconductors, and the point is that this is more or less narrow. This is hematite, this is titanium oxide, this is, I mean, there is a different there are reasons that they think that hematite can be the one that
See, and so you looked some band gap, which is not too large, but neither too close, right? Something.
Now, there is a things that they do know about this process of oxygen evolution reaction. Here is the most accepted model for the evolution of the reaction that you started. You have hematite that is an oxide, iron oxide, but when you are in contact with water, then in the surface, you don't have exactly this hematite, but you have a kind of hydroxide of iron hydroxide. So in the presence in water, you have this species. But when you put the potential and light, it seems that there are 4 species because of a reason of you need to give 4 holes so you can have 2 molecules of water. I mean, I won't go in detail on that, but the point is that they do know very well that there should be 4 holes to get 4 reactions, so you have the water for chemical reasons. So, but they are not very sure which are the species, the intermediate species. They do believe very strongly that this species is the next one or exists. That this is another iron oxide. We call it double bonded iron oxide, and they think that this is the normal process. This is what is mostly accepted. There have been studies that you can, when this reaction is happening, there have been infrared or spectroscopy studies that, and another studies that it seems that what you can see as metastable state is this guy, the number 2, that we call double bonded oxygen. Now I will tell you the last part of our research. We gave evidence to think that maybe this is not the process. This is a cyclic process of 4 steps, but that maybe the process is a combination of 2 different processes that work parallel. And we put in our study, the result is that we have evidence that maybe the second one is that we have 2 different cycles that works parallel, and that it could be A or B. Some of these species is the species of this double bonded oxygen that the people have observed in laboratory. I will tell quickly the main ideas of the talk, so I cannot extend much more, but that was the point. These are our own experiments. Here in the black one is how evolves the electricity with light. Here in the horizontal axis, you can see how the potential, you increase the potential, so you start here to have the reaction, and goes the current goes up, and that's it. Now with no light is this purple with a dashed line. If I do more with more potential, this purple goes up like from here, but it's not in the plot. Now there is 2 different experiments that is a combination of light or no light. One is have the same. You make a sweep of the potential going up, but you turn on and turn off the light, and we call the chop light. And there are interesting things that you can see there, because here you turn the light and it goes some reactions and then goes down the reaction, and you turn off the light and you have this negative current. And I will tell you that this is information that I will tell what does it mean, but it tells new information of some states or some species that are there but still the cycle is not complete. I will tell a little bit.
So, but the meaning of negative current, it's like you're gaining electrons from the water?
Exactly.
Okay.
Exactly. Is that when the holes have reaction with the water, it means that there is a positive transfer of charge. So you will have this positive current. But if you transfer electrons from the anode to the water, you have the opposite. And this happens if you have, instead of an oxidation reaction here in this line, we will have oxidation reactions in this sense. But you could have a reduction reaction that is opposite, and this reduction reaction will have an effective charge transfer, but with the opposite sign. And it will be something similar that you give an electron to the electrolyte instead of give a hole. That's so. Another experiment is that you put, like we put here in this potential, when we have with light, we put it a lot of time here, and then we turn off the light. And when the light is turned off, so we don't have the reaction of, because here with no light, you don't have the reaction. But first, when we turn the light, we have this. So I will put with the mouse. We have here in this potential with light, we have this current, and then we have plenty, 1 minute, 2 minutes, we leave there. And then we turn off the light, and the current goes down, and then we sweep the potential downwards. And it happens this, it goes down, but then appears a current, a negative current. And what is that negative current? Where the people say that is kind of charge storage. They call it in that way. But there we had a lot of discussions in our group and say, no, wait, it's because it's a way to say it, but really it's not that you have charge storage. They say that they were trapped holes. But I say, well, no, this, if they holes and they are transferred to the electrolyte, you should have positive current, not negative. Because if what you have trapped are the holes that are positive, if they are transferred to the electrolyte, you should have positive current. But they say, no, it's not that they are trapped holes, but they are this species. You have molecules of this species, and when the potential is down, when you reduce the potential, you increase the amount of electrons that are in the material. Because if you increase the potential, all the electrons goes away. All the electrons separate goes to the cathode. But if you really reduce the potential, then you have more free electrons. And if you have more free electrons, you can have a reduction reaction from this species to the other. So my partners, they told me, yes, we understand this, but we call these trap holes. And not the same holes that I told before. It was something of the material science and the physical. This one?
So what are the meaning of these lines? Is because you were
these ones?
About, no.
These
U ones, the U ones that cross all the yes. Because you were talking about some time that you start with this condition, then you change it, then you
yes.
Is that
okay?
The stamp where that process happened, or
the lines that I put, yes, this is a nice observation. These lines only was a kind of reference in the sense that here we have a potential when we have no current or almost no current when in the water photo-oxidation, and here we have kind of in this potential, the tree, we have kind of I don't remember the word, that is it's like saturation of the current that you can have, and we have an intermediate part that is that it's here. So here I put a potential of with almost there is no current or no the reaction. We have some reaction, and here we will have everything. And saturation, it means that it seems that we are taking all the holes are reacting, and all the holes are being transformed to the reaction. And here is not the case. And then that's why we only put like references, because this reference we will lose it next. But the point here is that, I mean, one of the keys is this blue line that we call cathodic discharge measurements. And this is the key part to get information. At the beginning, I was calling the research to do simulations of this curve of the photo-oxidation, that is this type of curve. But I had a lot of discussions and things of how to fix parameters and how to calculate what is the current and everything, because to calculate this current, I had to calculate how are the reactions of different 4 species, and I have reactions, the oxidation, I had reaction of negative, like these reduction reactions, and I had to take into account the arrival of holes, and it was a mess to know how to fix the parameters or how to yes, which parameters I can rely on, or I can
My question was a little bit different.
Uh-huh.
The meaning of the chart. And
Uh-huh.
we see them
Yes.
because this short line means like well, something is spinning, I think, and sometimes the light goes through this thing, and sometimes it's cannot pass because there is some obstacle. And then you see a sequence of these lines, and when it's when light reaches the objective, then you see those lines. Is what I
No, like the gray lines. All these gray lines.
yes.
Uh-huh.
So my question is the potential is like a proxy of the time, or
Yes, the potential is linear with the time. You have a sweep with constant velocity, the sweep of the potential.
okay.
Yes. So the point is that I try to get parameters, but I say no, but before I see the parameters of all the reactions with the oxidation reaction that goes forward, let's simplify the trouble. I mean, not the trouble, the problem. Let's simplify the problem and do it only without light. And if I have no light, I should have only reduction reactions. And maybe let's try to get information only with reduction reactions. So I was focused only in this type of information. Because here, you turn off the light, you have some species, and you move the potential, and you get some information. But you know that this information is not for the forward reaction, but for the reaction that goes backward, these reduction reactions. And that's what the main idea. I made some simulations. Well, not before that, I will show this later. There is a very standard procedure that is called three-step cathodic discharge measurement. Is in this way you put your in the vertical. Now we have in the vertical axis we have potential here. So you put a potential fixed in a high potential, and at some time you make a sweep of the potential down, and that's it. This, for example, with light here in the blue, and you goes down, is exactly and here is the current that you get there. When you have a high potential, in this case is near to 1.5, the current is high, then the light is turned off, and when you turn off the light, the current goes almost to zero, and then and this time at this second you sweep the potential down, and then you get this negative current. This blue process is exactly the same, and this one, but it's a different representation. But the process is this. The interesting part is that if you go to in a middle range, you do the same, and when you turn off the light, you have a small peak here that you can see, and when you make the sweep, you have all this peak. But if you start with a much smaller potential, you have the peak when you turn off the light, but you don't have. I mean, you have this peak, but you don't have the other wave in the other part. So, previous that I arrived there, the experimental group say, okay, we know that these are what we call trap holes, that are species that goes and make a reduction reaction. But they say, we have two different types of trap holes. They call the stables and the unstables. They say that the stables are these ones that reacts with the potential, and they have that they say that they have unstable ones that are these ones that quickly reacts with the light. But they couldn't explain, so I say no, this is strange. Why we will have two different nature of holes or trap holes? So what I did is to make simulations, and I showed in simulation that this could be possible only because a different behavior of exponential behavior, because when you have lower potential, you have much more electrons there, and the quantity of electrons increases exponentially with the potential. So this can, if you have much more electrons, you can have more quickly reduction reactions. So, but if you have a big potential, then you don't have almost anything. No, you don't have no electrons there, so you don't have reduction reaction. And when you start to sweep, then the electrons start to come, and you have these reactions. That was the type of mechanism. I made simulations. At the beginning, everybody looked with the skepticism, which is right to do it in science. But then I show more things, and then everybody was like kind of shocked, and they said, "Okay, let's go for that direction." But let's do the experiments now, other experiments. So we try to think in a different way. I propose first. I say, okay, if you want to believe it or not, I propose different protocols that haven't done never. I mean, that's one of the nice part of this research, that we made different protocols. This is unstable holes or stable holes. The protocol that I proposed was this four-step cathodic charge, and I told them, look, I think that is the same nature. That it doesn't have with light or potential. So what you are going to do is the 3 experiments start with the same potential, big potential. Then you turn off the light, and all the 3 are with high potential, and all of them we're going to have high current. Then at some point, what you do is abruptly you reduce the potential abruptly, and let's see what happened. The point is that when they do that, the biggest jump is the green one, right? Okay, that's why the green one we have this big decay, because we have an abrupt reduction of potential. A lot of electrons arrive, and as a lot of electrons arrive, they have this big peak, and you have all the reactions. You make that the reduction reaction of the species goes much quickly. But this species that is the number 2, the species number 2, reduces, so you deploy all the species quickly. So you have a decay, a kind of exponential decay. But if the potential you reduce only a little bit, you don't have electrons, so you do not have depletion of this species. So until you make the sweep and you get more electrons, you have this depletion of the species. You have that was the explanation. But now here you can see clearly that it's not the light, that this has to do with the potential, and so that's one of the first. And the next, they said that this was a stable hole that only reacts with potential. I said no, the reactions, the dependency of reaction is exponential. Maybe you have your exponential rate of the reduction reaction, maybe it's very small and you cannot see it, but it should be there. It's not that there are no reaction with high potential. So what I propose is try to do, or no, maybe Anton proposed that. I don't remember that, but the point is try to do the sweep of the potential not at the first second. Do it at 2 seconds or at 3 seconds or more, and see if you do it in more time. See if the size of this guy is the same. So you can see this. This.
We see the question.
Yes.
What is the time? What is the value of the potential in the lowest point of the current density?
The potential here.
In the orange and in the blue one. The lowest points, like the value. What is the value of the potential?
Here we start to sweep.
I am interested in the point of the deepest sure. So
here.
Yes.
I'm not sure, but I will show a relation. I will show the relation about that.
It seems like it's more related with the value of the potential.
Yes, of course. Of course, because there is a potential that the reactions like that. Yes,
confirming your hypothesis.
Something like that. Yes, it's not exactly, depends on more things, but it's very similar. Yes, I will show.
What?
Exactly. So
Yes.
this curve, if we put it in different scale, is this one. But if we repeat the experiment and instead of starting the sweep at the first second, we do it at the second and the second 2 or the second 3. I mean, here is like the second 10. I don't remember exactly how many seconds. Here this was 10, 20, 30, 40. The size of the So this was reducing. So this is one of the things that confirm the idea that the reactions are happening, but they are so slow that you cannot see it. So if you wait and you do not sweep, the reaction is still happening, and then the species transforming to the species one, because you have a reduction reaction, but very slow. So you cannot see the current. But when you make the sweep, then a lot of species transform, and you see it, but there are less than before. So this is an experiment that never had been seen before. But there was another strange thing. Look, the shape of this thing. Start to see it's not a single peak wave. It seems that there are two peaks. Here is at the second 100, but I will show the next ones. At the second 110, 120, 130. Look this shape. And this was also a kind of shock result, that there are two peaks. And the two peaks, it means that probably there are two species, like two metastable species, and it's something that no one has reported before. And that's like one of the experimental results that we have. And now, what is the rate of decay of these peaks? So I experimentally compared that we have different rate of decay, but they are more or less of the same order, the decay rate of those peaks. So my proposal is to say, okay, do we have two species? Maybe we can explain it because of these two species, but it could be in two different ways. We start with a species A that reduces to species B, and here we have a transfer of an electron, and from species B reduces to the ground when we have no potential at the end. Or maybe we have this type of thing. We have a species A that reduces to some ground, and another species B that reduces to some other ground, like in parallel pathway reactions. And at the end, we have like theoretical results to think that this is the parallel pathway, the right one. And that's the important result here. And what is the implication? If you have two parallel processes, maybe you don't have a cycle, but maybe you have the parallel processes because from A goes back to G, and from the other B goes back to G also. Not only from A to B and from B to G. And that's the main, the possible main implication. Now, this was modeling in this way. I won't go into that, but the total current will be a summation of two currents. Each current comes from each different reaction. This is the reaction from A to B, and then the reaction that starts from A and the reaction that starts from B. And the reactions has to do with the concentration. If you have concentration, if you have some more concentration, you have more reactions, of course, and you have more current. And the density of electrons is, as I told you before, is exponential with the potential. If the potential is lower, you will have more density of electrons. And this is a compartmental model, and you have two different equations, ordinary differential equations, and you have an evolution of this. The type of results is like that, like this. We have the contribution of reaction A and the contribution of reaction B, and at the end you will see this current. That are the two of them when you have a linear sweep in the potential. And these are the results, theoretical results for serial and for parallel, where we have the three types of behavior. When you have only a peak, or we have a peak and this wave, or we have only the wave. In both, we have some kind of these three general behaviors, but how to decide which one is? And the idea it was about the relation of the peaks, that one peak decays, what is the relation between the heights of the peaks? And the general idea was that the second peak, you never see it bigger than the first one. That's why the general idea. I won't go into details because we have made a lot of time, but In simulations, for the serial pathway, the second peak is always bigger. This is the ratio between the peaks, and the peak of B, the second peak is always bigger than the peak of A. And for parallel pathways, you can have second peak bigger or first peak bigger. You can have both options. So that's kind of the main reason. So if we cannot have in this model that the second peak is smaller, then we discard this model, and this model do allow the things that we observe. And this is a simulation with a parallel model, how this peak with different sweep times behaves. And you have a kind of change of the size of the peaks, and which is consistent with what we see. Here are the concentration of the concentrations of the species at different times. So at the beginning, you have some proportion of A and B, and as the time goes up, when you make the sweep very early, that is the first case, you make the sweep at the first seconds. So here you make the sweep, so everything transforms into G very quickly. But if you do the sweep intermediately, then everything turns to G here. Or if you take more time to do the sweep, happens here, and you have these different peaks for each one of the three parts. And well, this is another with this technique of the four-step cathodic discharge measurement. We can also estimate the concentration of the initial concentration, but I won't tell more about that because it's more specific. And I only finished that, like, three main ideas. This is that water splitting by photocatalysis could be something pillar for energy technologies in the future. Maybe it could be something, and I think that it will happen, this transformation. But the point is that nowadays is not yet understood, and there is a lot of effort at different levels. There is effort in things, fundamental things in quantum stuff, in computational chemistry, in classical or semi-classical stuff. I don't know, in different scopes, there is a lot of efforts trying to get to contribute to the topic. And in our study, we provided evidence. We will have to see that there is more evidence that provide to the same sense or not. But we provided evidence that maybe it's not this serial process that everyone thinks that occurs with hematite, but that maybe there are two parallel processes. And hopefully, this knowledge will contribute to understand better the process. And that's it. Sorry and for the time. But
Thank you.
thank you.
Thank you, Paulino, for your very interesting talk. Does anybody have a question?
Okay. I have several questions. First of all, the light you were talking about is visible light, right? Yes. So I understand that when there is no light and you see the negative current, but your rate of photo analysis, rate of electrolysis, that is higher when you have light, or that's lower?
I'm looking. Let me put a diagram. I'm not sure if I understood the question, but let's see step by step. Here, like, if there is no light, your current goes in this potential.
That is also true for in the presence of him.
Yes, like with hematite in our particular experiment.
Yes, in your experiment.
Here with no light, you have zero current, and the current start to rise like in this, like with 2 or 2.1 in the potential. Like here start to raise the current.
Your negative current, that means, is not helping anything with your electrolysis.
No, actually it's not helping. It's the point. Look, this region happens here because it's the opposite of helping. It means that you have a lot of reduction reactions. So if you want that the complete cycle for water, for the oxygen evolution reaction occurs, but sometimes you transform in your cycle to one species, but then there is a reaction that goes back to the other species, so you don't have the reaction that you want.
But in the presence of your hematite, your when you have light, the presence of the hematite, your electrolysis is higher, right?
Yes.
So that's very counterintuitive, right? Because you're negative. Okay, you are explaining that the negative current is basically happening for these trapped holes in your hematite, right? And now that's not helping your electrolysis. Now, in the presence of electrolysis and light, your amount of electrolysis is higher than when there is no hematite.
Yes, but it's because I mean.
So basically, hematite is helping in one sense. In that sense,
Totally. I mean, due to hematite, we have the rise of the reaction happens with much lower potential.
That means it's helping.
Yes, of course it's helping, but we need even lower.
Yes.
We need that
less energy in that sense.
And look in this plot, you can see these spikes that you see here. It means that you have holes in the surface because you start having reactions that go forward reactions because there are transfer of positive charges to the electrolyte here. So you can reduce that. I mean, we expected that the reaction occurs here like in 0.8 because it seems that is possible, but we don't have it. We have the reaction in this part. So the point is that it's not happening because we also have reduction reaction. If you have power oxidation reaction that goes forward, what we want, but we have oxidation reaction and you transform the original iron to the next iron, and then you have a reduction reaction that transfer a negative charge and stop the cycle to occur. What we want is to avoid this type of reduction reactions. So all the cycle is completed even in a lower potential than this one. And I don't know.
You're saying that basically the presence of hematite is helping your electrolysis, but the reduction reaction which gives you the negative current is the mechanism which is opposing the electrolysis.
Yes.
So if you can reduce this negative current or this reduction reaction, then the presence of your hematite will be even more helpful.
Exactly. And this is the aim, and it's exactly the aim of everybody how to hack this. We want to hack this type so we can take advantage on all the holes that are to the surface.
Yeah. How did you know that? I mean, because in a first sight, I would think that because you are in a so low potential, maybe you don't have enough holes to start this electrolysis. That's why you see. I mean, you have holes, but maybe they are not enough to produce a large current, for example, to start this electrolysis. How you know it is not because you have very few holes, and it is because of this backward reaction you are having.
Okay, yes, it's a very good question. First, even if there are few holes, if we have with low potential, then it's like the trees. The trees have no a very big efficiency of the transformation of solar energy. But the important part is that the efficiency is like 1%, 2%. I don't remember the number, but it's very low efficiency. But they do not care because they have sun. I mean, it doesn't matter that the efficiency is not very big because the sun is free. So the important is that they can do it with the available resources that they have. And this is so. In this case, the point is not that if you have few holes, but that you take it with a small potential. And how do we know? Because here there are holes that you know that they are making they are making the reaction oxidation because they are transferred, but they cannot continue
Going to
the cycle and maintain the current here because they have reduction reactions. So we can see that we even can if with the engineering and science goes forward in this direction, maybe we can get the reaction from here. And then if we can advantage of all the holes, and they can do it now, it can be done with something that they call hole scavengers. Sometimes, for example, a hole scavenger is peroxide, like agua oxigenada. They put it, and they can get all the holes. They have done it like that. But the point is that they want to do it only with water, because also it's a problem to have another substance that you have to produce to get. I mean, you have to produce the whole scavenger and then do the other, and this is also a thing that takes energy. I mean, it's
One more question, maybe it's a stupid one.
no.
So once you have the electrolysis, how much amount of hydrogen you have? My point is that you have an input of energy for this electrolysis. Now you gather some amount of hydrogen, and if you burn that hydrogen, get back water again. So you will for the present scenario, will you generate more energy than that or less energy? How much is that ratio?
I'm really not sure because I haven't been into things like for the real implementation. Probably I don't know.
Because if I think in language of energy conservation, right, and you have water and you do electrolysis, so the amount of energy what you need to electrolysis the water to get this hydrogen, and then if you burn that hydrogen to get back water, that amount of energy cannot be higher than the amount of energy you are putting.
Yes, no. The point is that you get energy from the sun. In this case, an open
Because of your
system.
light.
Yes,
And your hematite may be trapping some energy.
Of
So
course.
these two things are free.
Yes. That's
So that efficiency is not known till now. How much energy you are putting by yourself and how much
Exactly.
energy you are getting back.
exactly.
So that's
Yes. Mm-hmm.
Yes, Thomas?
If I understood this correctly, these spikes we see, these are just symbols, right?
Are just
They
what?
symbolize that you have short time light intensity. I mean, peak. What is it called?
Yes, yes. I mean,
But what is the time scale of this peak? I mean, because the line, the horizontal line is really potential. So these are not spikes in potential; they are spikes in time.
yes.
So it's just to symbolize the spikes, right?
I don't remember the like usually the sweep. I don't remember the time in which you sweep from here until that, but this is kind of 1 minute, 2 minutes, something like that to do the whole. This is on that order.
So these spikes are, say, maybe a lot of milliseconds, right?
Something like that.
I mean, it's not nanoseconds,
No,
picoseconds,
no.
or something. What you do in laser physics, right? And then, do you know with what this time scale is related? Or
With the velocity of the reactions, because what is happening is that, I mean, in this model, what is happening is that you have this species. You start to increasing the potential and you put light, so you make an oxidation reaction of a species. So you have oxidation reactions, but before that you have another oxidation reaction, you get a reduction reaction. And when you this sometimes like what happens sometimes is that here you have more in this next step from 2 to 3, the velocity of reaction is slower. You need more potential to jump from 2 to 3. So you increase the potential, a lot of molecules transform from 1 to 2, but here in 2 they get stuck. And no, really.
no, I mean, the problem is you have these electrons, they must somehow, what is it? I mean, they must diffuse right from the cathode to the anode. So you're saying, for instance, that
if the potential is not so big, not too much. If the potential is slow, you still have a lot of electrons. You need to increase more the potential, so all the electrons diffuse and then goes to the
diffuse, but this diffusion time, this should be the time scale.
probably. I'm not sure. Yeah,
So
probably
it's not really the reaction by itself, because the reaction is, so if you have the photon, then the photon hits and it happens, right?
But not the reaction is not when the photon hits. The reaction is when the hole arrives to the world, to the surface, and you had absorption.
Yeah,
When you have absorption of a molecule, then you have a molecule that was this species one and transform it to.
So you need the electron, say, to move
The electron has
over space, right?
Yes, the electron
So it's a geometric problem. It's not just that of the chemical reaction. It's really for the charge to be in the right place. At the
yes, yes.
It has to,
No,
has
but
to move.
but not only, also it's chemical because you have a probability of the reaction to
Okay, so
occur.
there are the two parts. Of the
Yes. And the probability changes exponentially because of the activation energy of the reaction. So if you have more electrons, the probability increases.
Yes, but you need time to get the electrons to the place.
Yes.
And that is what
But
makes
they
the
are
time
there.
scale.
But the electrons are there. Sometimes if you increase the potential, you get rid of electrons. Your density of
So that
electrons
you get rid of
reduces.
the electrons.
Huh?
Where do they go, the electrons? If you say you get rid of the electrons,
So
where do they go?
To
The
the
thing
other
is-
side, they drift. When the potential is very high, like with the potential is like in this part, then you almost have no electrons.
Where do they go?
Then they go they transport to the other side, to the cathode.
Yes. So again, so it's really diffusion and time scale of what happens is controlled by diffusive processes in space.
Yes, but for example, here,
The chemical reaction.
yes, but for example,